At the end of this video, you should be able to convert measurements into scientific notation and distinguish between inversely and directly proportional relationships. In scientific notation, numbers are written in the form m times 10 to the nth power, where the factor m is a number greater than or equal to 1, but less than 10, and n is a whole number. For example, to write the quantity 65,000 kilometers in scientific notation and show the first two digits are significant, you would write 6.5 times 10 to the fourth kilometers. Writing the m factor as 6.5 shows that there are exactly two significant figures. If instead you intended the first three digits in 65,000 to be significant, you would write 6.50 times 10 to the fourth kilometers. When numbers are written in scientific notation, only the significant figures are shown. Suppose you are expressing a very small quantity, such as the length of a flu virus. In ordinary notation, this length could be 0.00012 millimeters. That length can be expressed in scientific notation as it is on the screen here. 0.00012 millimeters is equal to 1.2 times 10 to the negative fourth millimeters. We move the decimal point 4 places to the right and multiply by the number 10 to the negative fourth. 1. Determine m by moving the decimal point in the original number to the left or to the right so that only one non-zero digit remains to the left of the decimal point. 2. Determine n by counting the number of places you have moved the decimal point. If you moved it to the left, n is positive. If you moved it to the right, n is negative.
Scientists sometimes need to express measurements using numbers that are very large or very small. For example, the speed of light through space is about 3 billion meters per second. 9 zeros is a lot of zeros to keep track of when performing a calculation. You can express values as a number multiplied by a power of 10. This is called scientific notation. There are 9 decimal places to the right of the 3 in 3 billion. So using scientific notation, the speed of light through space is written as 3 times 10 to the 9th meters per second.
Addition and subtraction. These operations can be performed only if the values have the same exponent, meaning n factor. If they do not, adjustments must be made to the values so that the exponents are equal. Once the exponents are equal, the m factors can be added or subtracted. The exponent of the answer can remain the same, or it may require an adjustment if the m factor of the answer has more than one digit to the left of the decimal point. Consider the example of the addition of 4.2 times 10 to the fourth kilograms and 7.9 times 10 to the third kilograms. We can make both exponents either 3 or 4. The following solutions are possible and shown on page 51 of your text or at the bottom of the screen here. Note that the units remain kilograms throughout the calculation. Multiplication. The m factors are multiplied and the exponents are added algebraically. Consider the multiplication of 5.23 times 10 to the 6th micrometers by 7.1 times 10 to the negative 2 micrometers. Note that when length measurements are multiplied, the result is area. The unit is now micrometers squared. Division. The m factors are divided, and the exponent of the denominator is subtracted from that of the numerator. Note that the unit for the answer is the ratio of grams to moles. Learning to analyze and solve such problems requires practice and a logical approach. In this section of the lecture, you will review a process that can help you analyze problems effectively. Most sample problems in this course are organized by 4 basic steps to guide your thinking and how to work out the solution to a problem. Step 1. Analyze. The first step in solving a quantitative word problem is to read the problem carefully at least twice and to analyze the information in it. Note any important descriptive terms that clarify or add meaning to the problem. Identify and list the data given in the problem. Also, identify the unknown, which is the quantity that you are being asked to find. Plan. The second step is to develop a plan for solving the problem. The plan should show how the information given is to be used to find the unknown. In the process, reread the problem to make sure that you have gathered all the necessary information. It is often helpful to draw a picture that represents the problem. For example, if you are asked to determine the volume of a crystal given its dimensions, you could draw a representation of the crystal and label the dimensions. This drawing would help you visualize the problem. Decide which conversion factors, mathematical formulas, or chemical principles you will need to solve the problem. Your plan might suggest a single calculation or a series of them involving different conversion factors. Once you understand how you need to proceed, you may wish to sketch out the route you will take, using arrows to point the way from stage 1 to the solution in the next part. Sometimes you will need data that are not actually a part of the problem statement. For instance, you'll often use data from the periodic table. Compute. The third step involves substituting the data necessary and conversion factors used into the plan that you have developed. At this stage, you calculate the answer, cancel units, and round the result to the correct number of significant figures. It is very important to have a plan worked out in step 2 before you start using the calculator. All too often, students generate final answers that are not in the correct units given the problem. Evaluate. Examine your answer to determine whether it is reasonable. Use the following methods when appropriate to carry out the evaluation. 1. Check to see that the units are correct. If they are not, look over the setup. Are the conversion factors correct? 2. Make an estimate of the expected answer. Use simpler, rounded numbers to do so. Compare the estimate with your actual result. The two should be similar. 3. Check the order of magnitude in your answer. Does it seem reasonable compared to the values given in the problem? If you calculated the density of vegetable oil and got the value of 54.9 grams per milliliter, you would know that something is wrong. Oil floats on water, therefore its density is less than water, so the value obtained should be less than 1.0 grams per milliliter. 4. Be sure that the answer given for any problem is expressed using the correct number of significant figures. Look over the following quantitative sample problem. Notice how the 4-step approach is used in each, and then apply this approach yourself in solving the practice problems that follow. Calculate the volume of a sample of aluminum that has a mass of 3.057 kilograms. The density of aluminum is 2.70 grams per cubic centimeter. Analyze. Givens. Mass is equal to 3.057 kilograms. Density is equal to 2.70 grams per cubic centimeter. Unknown. The volume of aluminum. Plan. The density unit in the problem is grams per cubic centimeter, and the mass given in the problem is expressed in kilograms. Therefore, in addition to using the density equation, you will need a conversion factor representing the relationship between grams and kilograms, which is 1,000 grams is equal to 1 kilogram. Also, rearrange the density equation to solve for volume. Compute. The answer should be rounded to 3 significant figures. Evaluate. The unit of volume, cubic centimeters, is correct. An order of magnitude estimate would put the answer at over 1,000 cubic centimeters. 3 divided by 2 multiplied by 1,000. The correct number of significant digits is 3 to match the number of significant figures in 2.70 grams per cubic centimeter. Two quantities are directly proportional to each other if dividing one by the other gives a constant value. For example, if the masses and volumes of different samples of aluminum are measured, the masses and volumes will be directly proportional to each other. As the masses of the samples increases, the volumes increase at the same rate, as you can see from the data in Table 2-7, which you can find on page 55 of your text or on the next slide. Doubling the mass doubles the volume. Halving the masses halves the volume. When two variables, x and y, are directly proportional to each other, the relationship can be expressed as y alpha x, which is read as y is proportional to x. The general equation for a directly proportional relationship between two variables can also be written as is shown on the screen here. The value of k is a constant called the proportionality constant. Written in this form, the equation expresses an important fact about direct proportion. The ratio between the variables remains constant. Note that using the mass and volume values in Table 2-7 now gives a mass-volume ratio that is constant, neglecting measurement error. The equation can be rearranged into the following form. Y is equal to kx. The equation y is equal to kx may look familiar to you. It is the equation for a special case of a straight line. If the two variables related in this way are graphed versus one another, a straight line or linear plot that passes through the origin at 0, 0 results. The data for aluminum from Table 2-7 are graphed in Figure 2-11 on the screen here. The mass and volume of a pure substance are directly proportional to each other. Consider mass to be y and volume to be x. The constant ratio, k, for the two variables is density. The slope of the line reflects the constant density, or mass-volume ratio of aluminum, which is 2.70 grams per cubic centimeter at 20 degrees Celsius. Notice also that the plotted line passes through the origin. All directly proportional relationships produce linear graphs that pass through the origin. Two quantities are inversely proportional to each other if their product is constant. An example of an inversely proportional relationship is that between speed of travel and the time required to cover a fixed distance. The greater the speed, the less time that is needed to go a certain fixed distance. Doubling the speed cuts the required time in half. Halving the speed doubles the time required. When two variables, x and y, are inversely proportional to each other, the relationship can be expressed as follows. Y alpha 1 divided by x. This is read, y is proportional to 1 divided by x. The general equation for an inversely proportional relationship between two variables can be written in the following form. xy is equal to k. In the equation, k is the proportionality constant. If x increases, y must decrease to keep the product constant. A graph of variables that are inversely proportional produces a curve called a hyperbola. Such a graph is illustrated in Figure 2-12 or on the screen here. When the temperature of the gas is kept constant, the volume, V, of the gas sample decreases as the pressure, P, increases. Look at the data shown in Table 2-8 on page 56 of your text or on the screen here. Note that pressure multiplied by volume gives a reasonably constant value. The graph of this data is shown in Figure 2-12.
Two variables are directly proportional when their quotient is constant. In this example, when we divide the mass by the volume, we get a constant. From the graph, we see that when variables are directly proportional, when one increases, so does the other. Two quantities are inversely proportional when they have a constant product. In this example, when we multiply the volume and the pressure, we get a constant. From the graph, we see that when variables are inversely proportional, when one increases, the other decreases.
At this point, you should be able to convert measurements into scientific notation and distinguish between inversely and directly proportional relationships.